Hello, everyone. I'm here with NASA's Goddard Space Flight Center in Maryland. When NASA launched its X-ray telescope aboard the Imaging X-ray Polarimetry Explorer, or XPE satellite, in December 2021, scientists hoped it would reveal new insights about black holes and neutron stars, but no one expected it to uncover secrets of a much more familiar celestial body, our Sun. 1 year into its mission, the orbiting observatory has made an astonishing discovery of sulfur deep in the Milky Way galaxy. The detection was completely unexpected. No one was looking for sulfur, which is highly unusual because this element normally burns away into space after stellar explosions called supernovas. XRISM principal investigator Brian Ramsey of Penn State University said in a statement, "We weren't really sure what we would find when we started this mission. There are so many things that could be emitting X-rays out there. We chose to look at these sources with the idea that we might be able to learn something about a wide range of objects." The discovery was published in the journal Nature Astronomy on July. Co-author Fiona A. Harrison, professor of astronomy at Caltech, said in the statement, "We were all shocked. We looked at each other and said, 'Are you seeing what I'm seeing?' It was very exciting." So how did a spacecraft designed to detect X-ray emissions from just beyond our solar system discover an element on our home turf? And why is the detection of sulfur so surprising? The answers lie in IXPE's instruments and its targets. IXPE was built by NASA in collaboration with the Italian Space Agency. It carries 3 instruments to observe X-rays emitted by matter at incredibly high temperatures. The first instrument is a mirror-based X-ray telescope that focuses light onto a 90-pixel camera called the X-ray Imaging and Spectroscopy Mission Telescope, or XRISM. X-rays can pass through most materials, including the hull of IXPE, but they can also cause damage at the microscopic level. To protect XRISM from this radiation, an adjustable shutter telescope where mirrors direct them to XRISM. Once focused, the rays hit a special glass called an X-ray scintillating fiber optic, which converts the rays into visible light, making them easier to detect with cameras. A second instrument, the X-ray polarimeter, measures the polarization of X-rays. That is the direction in which the waves of light oscillate relative to the direction the waves travel. Measuring polarization helps scientists better understand the nature of the X-ray emitting objects. For example, synchrotron radiation from a magnetar, a highly magnetized neutron star, will be partially polarized, whereas thermal emission from a hot white dwarf will not be polarized, unless it's influenced by a strong magnetic field. IXP's third instrument is the X-ray optics monitor, or XOM, which captures images of bright X-ray sources without the help of a telescope. Because it doesn't use mirrors, XOM is optimized to detect point sources of X-rays, such as magnetars. XOM works by placing a special type of plastic called a polyimide film over the top of an X-ray detector. Polyimide is opaque to X-rays, but it allows X-rays that pass through a small hole in the film to reach the detector. This detector then records the position of each detected X-ray. In order to see an object, any telescope needs to collect enough photons, the quantum of light. If the signal is too weak, the object will be invisible. To gather enough photons from faint objects like neutron stars and black holes, XPE must point its telescope in the general direction of the source for days at a time. But this means that while XPE is observing the faint source, the bright light from the galactic center may sneak in around the shutter and damage XRISM. So to prevent this, researchers programmed IXPA to avoid pointing its telescope at the galactic center, thinking that no interesting X-ray sources were there anyway. But after discovering sulfur, co-author Benjamin M. Morris of Northwestern University said, "It turns out that there are actually several interesting sources of X-rays in the galactic center. We happened to catch one with our net. As luck would have it, IXPE happened to pass within a few degrees of the galactic center during its commissioning phase, allowing it to snap a picture of the Sagittarius A East, or SGRA East, non-thermal X-ray source. Follow-up observations with the Canada-France-Hawaii telescope in Hawaii confirmed the source was in the galactic center. Other telescopes also tracked the source and showed it was located on the far side of the galaxy and moving away from Earth. All this information helped the team determine that SGRA East was emitting sulfur. But how did they make this unusual identification? In our galaxy, Supernovas occur when massive stars collapse at the end of their lives. They blast huge amounts of material into space, creating bubbles of gas that expand outward. These bubbles eventually run into the interstellar medium, or XRISM, the gas and dust between stars. As the bubble expands, it heats the ISM, creating a wall of very hot plasma that emits X-rays. Over time, the bubble's hot plasma cools, and the X-ray emissions fade. But the material expelled during the supernova can also produce a cloud of ionized gas. Unlike hot plasma, ionized gas does not emit X-rays. Instead, it glows in the radio band. After identifying SGRA East, the team turned to data collected by NASA's Chandra X-ray Observatory and the European Space Agency SXM Newton, which had observed the source in 2004 and 2005. By comparing these older images with the newer ones, they were able to rule out the possibility that the source was a wall of hot plasma. Then they examined data from NASA's now retired Compton Gamma Ray Observatory to see if a gamma ray burst had occurred in the region. This was also ruled out. Finally, they turned to the older data to identify the spectral lines of the X-ray emissions. Spectral lines are specific wavelengths of light. Atoms absorb or emit light only at very specific wavelengths corresponding to the energy levels of electrons in the atoms. So every element has a unique set of spectral lines that can be used to identify it. The team found that the spectrum of SGRAEs matched the spectrum of ionized iron and sulfur. The next question was, how did the sulfur get there? One explanation is that it came from a single supernova. However, this seemed unlikely because a single star would not produce enough sulfur to account for all of the X-ray emission. Another possibility was that the X-ray emitting cloud was the remnant of multiple supernovae, but the one that fit all the data best was that the cloud was the result of a star that exploded twice. Harrison said, "This is a rare event. Don't often see stellar explosions that happen more than once. All the mass in a star is in a narrow range, so it's hard for a star to explode more than once because the material gets blasted away during the explosion. But there are some models for how this could happen. Researchers think that in some circumstances, the core of a star can collapse twice. In a Type 1a supernova, the core bounces back and forth between collapse and rebound, leading to multiple explosions. Another scenario involves a close binary system in which a massive star explodes and leaves behind a white dwarf. The white dwarf then pulls material off a nearby companion star, igniting a second explosion. Cother Matteo Biguanazzi, an astrophysicist at the Italian Space Agency and the University of Rome Tor Vergata, said in the statement, "There are lots of scenarios that could explain it. It'll be interesting to try to figure out which one is correct." What happens next, though? The team estimates that SGRA East is about 80,000 light-years away. Scientists need to know the distance to calculate the luminosity of the source, or how bright it actually is. But because SGRA East is moving away from us at nearly 1 million kilometers per hour, it's impossible to accurately measure the distance. So even if IXPE could keep observing the source, its distance would remain a mystery. That's why the research team is hoping for a future mission. Morris said there's definitely a follow-up mission in our plans. I want to study this source in more detail and understand exactly what kind of event it is. In the meantime, the team is searching for other signals from SGRA East. We are still looking at data from our observations and are likely to find more interesting things that we have unseen yet. And this is only the beginning of IXPE's work, providing unprecedented opportunities to advance our understanding of exotic celestial objects and phenomena. To learn more about IXP, visit its page on NASA's website. While you're there, be sure to check out the mission's stunning images and videos. Thanks for watching.